Hello, my name's Alan Whittington. I'm a professor of geological sciences at the University of Texas in San Antonio, and I'm going to be talking today about recalescence in silicate melts. I'll share the screen so you can see my slides. My co-author today is Dr. Alex Selke of NASA Ames Research Center, California. So I'll start just by bringing us back to the classroom. Remember phase diagrams. This is a very simple one-dimensional phase diagram. So on the y-axis is temperature. And on the left side here, we see what phase diagrams normally look like because they are generally constructed very carefully with lots of experiments representing the equilibrium state of things. So at high temperature, we have melt. At low temperature, we have crystals. And in between, we either have a single melting point for a congruently melting compound, or for more complex melts in particular, we have a region of melt plus crystals between the liquidus and the solidus. So slow cooling takes us down through this diagram from melt to crystals. Whereas on the right side, we see what happens if we have very fast cooling, disequilibrium situation. We can go directly from melt all the way down to glass, completely bypassing crystallization. That transition here, the glass transition, I've shown as a zone rather than just a line because it doesn't happen at one specific temperature. It happens over a range of temperatures. Anyway, so if we start with a silica-rich lava, for example, or magma, if it cools slowly, it will end up fully crystalline, like this Himalayan granite on the left, make a lovely countertop. If we cool it more quickly, say it erupts from a volcano as lava and cools it quickly at the Earth's surface, then we're going to get a glass. So in this case, this is obsidian from Iceland. But these two rocks have almost exactly the same composition. One crystallized entirely, and the other one is almost entirely glass. Okay, we know that crystallization releases latent heat. So just as you have to put heat in to go from solid to liquid, the enthalpy of fusion, that is then released on crystallization. So one question is, how fast can that heat be released? And that depends on the kinetics of crystallization. So crystallization requires both nucleation and then growth. What we see here is a compilation of experiments from Phil Fenn in 1977, doing crystallization experiments on a hydrous feldspar melt, not too different in composition from the granite and obsidian we were just looking at. On the y-axis is nucleation density and also growth rate. The x-axis here is undercooling. So 0 at the left, this is the equilibrium, the liquidus temperature, where crystallization would start. And then we're going hundreds of degrees below that. And what we notice is that there's a particularly rapid spike in nucleation density at around 200 degrees of undercooling. So the further you can take your liquid before it starts to crystallize, the more rapidly it will then crystallize. And of course, you will get many, many very small crystals at that point. If you want a few large crystals, you cool more slowly. Just a few degrees of undercooling where nucleation is slow, but crystal growth is relatively rapid. And that does give a nicer looking countertop. Anyway, so we did some experiments. This is lava in a crucible, platinum crucible, just taken out of the furnace at about 1600 degrees, put down on a copper plate, and we're looking down straight into the crucible. The base is about 5 centimeters diameter. And what we're seeing is the lava cooling. Now in a second, it'll start over and we can watch it again. And what I want you to pay attention to is the relative location of red, which is hot, and yellow, which is even hotter. Okay, so the crystals begin forming around the edge of the crucible, heterogeneous nucleation. And now they start growing spontaneously in the middle of the liquid, homogeneous nucleation, and we see these beautiful spherical clusters of crystals growing. What's really important to note is that as these crystals grow, the hottest part is that yellow rim, the crystallization front. The next hottest part is the crystals that have just grown. And the coolest part of this whole thing is the liquid itself that the crystals grew from. So they spontaneously heated up as they grew due to the rapid release of latent heat. And this is a process known as recalescence, simply meaning reheating. So here are some stills from those experiments. Again, just taking lava out of the furnace, putting them on a plate, letting them cool. The key things to note, the crystallization front is hottest, that is the edge of the growing clump of crystals, but the crystals themselves, once they've grown, are still warmer than the melt that they grew from. Pretty cool. Just to prove this once again, now we're looking through an infrared video camera. So these are false colors that simply tell you what the temperature is based on the scale on the right side of the image, and that's in degrees C. So basically reds are around 1,000 to 1,200, and then anything yellow is hotter than about 1,250. Notice as the crystals grow, we see this wave of yellow spreading across the melt, which previously was an orangey red color. Okay, so our melt is now orangey red, and here come the crystals, and you can watch the crystallization front travel very rapidly through the melt. Okay, what does it look like when we pull the crystals out afterwards? Well, they look really cool in the electron microscope. You can see rapidly grown pyroxene crystals, these interesting herringbone structures, and similar structures are actually seen in rapidly cooled lavas as well. Okay, we can also quantify the heat release using calorimetry. So on the y-axis here is the apparent heat capacity in joule per gram per Kelvin, and on the x-axis is temperature. So if we start with our pyroxene again, we started with the glass, we heated it up, it went through the glass transition, the heat capacity increased, now we're liquid, and then it began to crystallize. And here we're just above TG, glass transition, a long way below the liquidus. And so here crystallization was very fast. And the heating was so much that actually the calorimeter stopped putting in any power at all, but the sample continued to heat. This crystallization peak extends to minus 58 joule per gram per Kelvin apparent heat capacity. And so basically we can just, the area of that peak tells us what the actual enthalpy of crystallization was, which was minus 277 joule per gram. As we continue heating our now fully crystalline sample, or mostly crystalline, we just chug along heating crystals up until we start to melt those crystals. We have at least two distinct peaks. The enthalpy of fusion here is about 432 joule per gram. And then by the time we get to 1500 degrees, we are once again entirely liquid. We can then cool the sample down, and that's the blue curve right here. And the enthalpy of crystallization here is minus 439 joule per gram, almost exactly the opposite of our enthalpy of melting, as it should be. And then once we've crystallized, again in two peaks, we're now crystals all the way back down to room temperature. One thing you'll notice is that the enthalpy of crystallization at low temperature is much less than the enthalpy of crystallization at high temperature. And this is as it should be, because the heat capacity of the liquid is higher than that of the crystals. So actually the enthalpy of crystallization or melting is itself temperature dependent. On the right, we see a similar experiment we did for a more complex melt called a komatiite. These are probably the kind of lavas that are erupting on Jupiter's moon Io at more or less the present time. And on Earth, they erupted in the Archean in the first couple of billion years of Earth history. Anyway, here we can see the actual value of the enthalpies is slightly different, but the overall pattern is the same. And again, of course, we can measure it being very reversible. So a few hundred joule per gram, which is quite a significant enthalpy. In the calorimeter, we're using much smaller samples. And we also see slightly different textures. You'll note in the calorimeter, we saw at least two different spikes on both crystallization and melting. And so the first spike was, again, growing these large pyroxene crystals, the dark gray, which is seen very clearly in the top left. But then the interstitial melt itself started to, well, I think it actually had some liquid immiscibility, And we grew tridymite, which is very dark in these backscattered electron images. And we grew some iron oxide, which is very light. And then this mid-gray is just glass again. Okay, now I'm going to show you a video of the chematite crystallizing. And the interesting thing here is that you won't notice it. So it actually already crystallized and you didn't even see it happen. It's all right, I couldn't see it happen either. I'm now going to show you how we know that it happened, apart from the fact that we saw crystals, of course, when we looked in the microscope. This is a different video. This is a 10-frame gap. So this is the temperature change over a 10-frame interval, which is about 1/3 of a second. And so our scale on the right side is now very, very different. Anything that is around this red-green boundary, actually in the red, is really not changing temperature from one frame to the next. Anything that goes yellow is heating. Anything that's green or blue, or especially purple, is cooling. So right there, for about 2 seconds, we see a heating signal cross over the base of the crucible. Let's just go back to it. It's cooling, and then suddenly right there, reds and yellows for 2 seconds. That was the crystallization of the chematite. It was very subtle when we were looking just in the regular infrared image. Okay, at the top here, this is the pyroxene. These are stills from the infrared image, just showing the yellow here of the crystallization front. And then for the chematite, yeah, we couldn't actually see it crystallizing in the video. But then when we looked at the difference from over a 10-frame or 1/3 of a second interval, then we could actually see it. And here's kind of a freeze frame of just of that crystallization beginning there at the margin of the crucible. So, but one thing to note here is that in the pyroxene, we go from reds to yellows. We heat by more than 100 degrees. Now, the software that comes with the camera can actually quantify this very nicely. The dashed lines here are focusing on 3x3 pixel areas. That's about 1 square millimeter. The solid lines average over the entire base of the crucible. Anyway, you'll see that in the space of less than 2 seconds, the pyroxene melt here heated by more than 150 degrees. The chematite melt heated by a little over 10 degrees, much harder to spot. And in fact, if you average over the whole base of the crucible, you don't really see any heating, but that's because the heating only affects one small area at a time. So spatial resolution is really important to actually seeing this happen. So the final question is, does this happen in nature? Well, here is my co-author, Alex Selke. Back in 2012, we were sampling these lava flows on the island of Hawaii. And we were at a place that about 17 years earlier, Laszlo Keste of the USGS had put some thermocouples in front of an advancing lobe of lava. And he saw the temperature, which is shown here, heat up rapidly as the lava hit the thermocouple. Then it would start to cool down. And then he consistently saw a temperature increase. And he suggested that it's possible that this was due to recalescence. This is the only reference to recalescence that I've been able to find in the volcanological literature. Recalescence happens best when you have very rapid cooling. So it's actually more likely to happen in a lava fountain, for example, shown here, than in a lava lake. And it may be particularly important, again, this is actually a photo of, or image of Jupiter's moon, Io, with an eruption happening there. So to summarize, on the left is a temperature crystallinity diagram. What we're trying to do here is to undercool quite rapidly, but without completely quenching to glass, and starting to crystallize at hundreds of degrees of undercooling, where we crystallize very quickly and can actually produce an increase in temperature. And on the right is a temperature time diagram, and basically depending on the size of the blob of lava you have in nature, it will either quench too fast, like a fragment of volcanic ash, or it might cool too slowly, like an entire lava lake. But droplets in a lava fountain are probably just right. Here are my conclusions, which I'll leave you to read. And if you have questions, please email me.